Hey, we're going to be finishing chapter 3 here, and we're going to be we're still looking at mechanical properties of materials and stress and strain relationships, and we're going to look at shear strain and shear stress today, and then the relationship between normal and shear, the modulus of elasticity, the modulus of rigidity, which we'll get into. But again, it's a lot of definitions. So I know this will probably be the last time you guys see this slide. You could probably recreate this on your own, but we just need to remember normal just means perpendicular to a surface. It doesn't matter how I cut it. It's that normal force, okay? We can have normal stress, that's the intensity of the force over area. And then we have shear. Shear is just tangent or parallel to a surface. And we're going to have shear stress with torsion. We can have beam shear. It's the longitudinal shear down the length of the beam, okay? And so we learned about strain, where we have some deformation, normal strain. We have that change in length per unit length. And then we had shear strain, where we don't have our perpendicular, our given perpendicular doesn't remain perpendicular. We have a shift. And again, think about a brake pad on your bike as you're braking, okay? So just like we had the tensile test that we talked about in the last video for normal stress, it's that force over area, we looked at tension. We could also have compression. I mean, we have to understand how materials behave in compression as well. We're going to have a shear test. We have to see how they behave when we apply a shear load. So remember, that's a force that's parallel to the surface. Okay, so the force is coming across the top. It's going to be parallel to that surface on the top, and it's going to cause that distortion. And we talked about the shear strain is an angle. And so when we have a shear test, it's still testing and we're trying to determine material properties, right? As we increase that force, that shear force, we're going to see an increase in deformation, okay? And we can plot it just like we did with normal force. We're going to have our stress, okay, up and down, and our strain, remember it's in radians, is going to be on the x-axis. So there are several different ways that we can do a shear test, and I've got a couple of examples of machines up here. So in the one in the upper right, you can see it looks like they're testing a glued connection. Okay, a glued connection. If you're a civil or construction or architectural engineering and you look at soils class or foundations, soil is also a material, and different soils are going to have different behaviors. So we're here on the bottom left, you can see they're doing a shear test on a soil sample. We build on the ground. We have to know how the ground is going to behave. Just like we did with the tensile testing, we're going to have that stress strain diagram, shear stress, shear strain, and we have very similar properties, okay? There's going to be that proportional limit where we have that nice elastic region that as we load and unload, we are constantly unloading back to that original shape, okay? There's not a permanent deformation. And then we get up to the yield stress, and we get up to ultimate stress, and then we have the breaking or rupture. So it looks, at least this caricature, is that the right word? Looks very, very similar. Okay, so we have that yield stress. Okay, we have that yield stress. That's going to be an important value, just like it was when we were looking at normal yield. Okay, we have the ultimate, that top peak, and then we're going to have fracture. Okay. Sorry, I keep looking at my dog because she had a procedure and I just took her cone off of her and she's so happy, and so I'm slightly distracted. I'm sorry. Okay. So when you have different soils, for instance, there might be densely packed, loosely packed. They're going to have different behaviors in terms of shear testing, okay? So let's talk about what is the shear modulus. So when we had stress strain with normal, pulling it apart, we had the modulus of elasticity. Where is the elastic region? What is the slope of the line? Well, with shear, we also have an elastic region. And this time we're going to call it, okay, it's going to be the letter G. and it is the modulus of rigidity, the shear modulus. It is also the slope of the line of the stress strain, okay, in the elastic region. It's just rise over run. You could take that, a stress in that region, you could find a strain in that region, divide them, you're going to get the slope of that line. So it is that change in stress over change in strain in the elastic region, okay? Modulus of rigidity, shear modulus, it is the letter G. So E is elasticity with normal. G has to do with elasticity when we're looking at shear, okay? So for this material, we just are drawing over from our stress, drawing up from our strain, and we can calculate. The units are going to be our units of stress, which are KSI or a Pascal, because when we look at strain, it's unitless. The normal strain was inch per inch. Our shear strain is in radians, okay? So we have units of stress, KSI, PSI, megapascal, gigapascal, Pascal times 10 to the 6th. Okay, you have to pay attention when you're looking in books to see how the value is given to you. Okay, so we now have shear stress equals G times shear strain. Okay, shear stress equals G times shear strain. And when we're looking in that, again, most engineered components are going to be designed to function within that elastic region. We don't want any permanent deformation to occur. And so it's just like what we did with the normal stress and strain. And if we're in that elastic region, then we know that it's small strains. And so if we're looking at the displacement over and we're doing tan gamma equals that change delta over L, we can just call it delta over L because of the small strains. Okay. So again, it's important to define that elastic limit where we no longer in the elastic region, and so we load and unload, 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 until when we unload, we don't come back to that strain of 0. We actually come back to, we now have a permanent set, okay? So it's the same thing that we did. So we now have these relationships. I have normal stress, so I have to remember normal stress is going to be change in length. Right now it's the axial load, that's all we've looked at. Stress equals E times strain. It's just the relationship of the slope in that elastic region. We have shear stress relationship. Shear stress equals G times shear strain. Again, it's in the elastic region, okay? And so the next thing we're going to talk about is Poissons ratio. So yet another new variable, okay? What happens when I stretch a rubber band? What happens to its length? Okay, the length gets longer. As I'm stretching that rubber band, what happens to its cross-sectional area? It's probably getting smaller, right? There's a relationship between the strain in the longitudinal direction and the strain in the lateral or tangential, the parallel, the cross section itself, okay? So if we are in tension, we are increasing in length, we're getting smaller, okay? We are getting a negative strain in our cross section. If we're compressing, okay, so we have a negative strain in our length, we're going to have a positive strain then, our cross-sectional area gets bigger. So we have Poissons ratio, and it is just the ratio of our lateral strain and our longitudinal, or you can think of it tangential and axial. Why is it negative? Well, if I stretch something, that's going to be positive strain. The cross-sectional area gets smaller, which is negative strain. So if I didn't have that negative, then I would have Poissons ratio would be a negative number, which is weird, okay? So we want Poissons ratio to be a positive value. So we just put a negative with that lateral over longitudinal strain. So as one is increasing, the other is getting smaller. One is increasing positive strain, one is getting smaller. One is getting longer, one is getting smaller, okay? So we're just looking at simple tension and compression here. We will talk about how to use Poissons ratio in an example. We're going to look at a wire that is the wire stretching. It has that nice change in length, that nice positive strain. What happens to the diameter? And we'll learn how to use Poissons ratio to calculate the diameter after we've applied the load. And then there's also a relationship between the modulus of elasticity, the modulus of rigidity, and Poissons ratio. And so if I know the modulus of elasticity and Poissons ratio, I can calculate the shear modulus. If I know E and G, I can get Poissons ratio. So this is just a nice little relationship between those three values. And we now have equations. So let's talk about these equations, okay? The equations above this line. We have normal stress, P over A, N over A, T over A, okay? C, compression over A. We have that stress equals E times strain in the elastic region. And we have strain as change in length over length. We haven't gotten to temperature change yet. We'll get to that in a couple of chapters. We also have Poissons ratio. Poissons ratio is the relationship between that longitudinal strain and that cross-sectional tangential lateral strain, okay? Shear. We have a shear relationship between stress and deformation, okay? Stress and deformation. And we now have a way to kind of put all of this together. So we've kind of exploded in the equation department. The nice thing is they're all very, very short and small equations. The tough thing is that in a problem, you may use these equations multiple times and you need to keep up with, is this the area of cable AB or the area of cable CD? What's happening with AB? How's that affecting CD? They may be different materials, so they're going to have a different E value, a different G value, a different Poissons ratio value. So you have to start really labeling things and drawing very clear free body diagrams. So join me in our next example. It should be the next video down.